عليكم ورحمة الله جميعا. Um, so let me share the screen for you. Okay, so the screen, let me open this file. Game theory. Last one was, it was what? Beyond the Nash equilibrium? Perfect coexistence. I think it was that, yeah. Okay, so last session we were stuck in some problem and we're going to have to solve it. We're going to have to figure it out together. Okay, let's go back. Let me share this. Okay, so let's review what we were doing. We were doing min-max, and originally what we did for min-max was we did it for one-time gain, but we realized that we also need to solve the problem for multi-games, which means we should consider a probability for each of the kicker and the goalies. And we need to solve it that way as well. So let's go back and see what we got here. So let's see. Okay, so we have a payoff table as follows. The payoff goes as follows. If the kicker goes left and goalie goes left, there's a 60% chance that the kicker will score, and there's a 40% chance that the goalie will catch. So that's why we see 0.6 gain for the kicker and 0.4 gain for the goalie. Okay, and if the kicker goes right and the goalie goes left, then there's a 90%, there's a very high chance that the kicker will score. So we write down a payoff of 0.9 for the kicker. And there's a 10% chance that he kicks it outside. So the goalie will have a 10% chance of scoring. That's why we give him 0.1 as the payoff in this situation. And similar material for the situations where the kicker goes right and the goalie goes left, and when the kicker goes left and the goalie goes right, and when both of them go right. Now, the goal was in min-max or in max-min. So, first of all, we want basically this is player 1, this is player 2. The kicker wants to maximize his payoff, and the goalie wants to minimize the kicker's payoff. Okay, so we're interested in a min-max problem or a max-min problem. Let's review that one more time. So in minimax, what happens is let's review the definition one more time. in min-max, what we do is that player player I's minimax strategy against player minus I in a two-player game is a strategy that minimizes minus I's best case payoff. So basically, in our situation, suppose we want to minimize best payoff for player 1. So player 2 wants to minimize the best payoff for player 1. So this is the basically minimax for player 2 against player 1. This is the definition. Minimax for player 2 against player 1 is that you first search over all the actions that minimize that maximize player 1's payoff, and then go after the actions by player 2 that minimizes that. All right, so that's the definition of min-max. Minimize player 1's best case payoff. Player 2 is going to play in such a way that will minimize player 1's best case payoff. All right? So in here, the goalie, which is a player 2 here, the goalie will act in a way that will minimize the kicker's best payoff. All right? So now we go back to our table. Minimize. Let's go back. So this one we're not involved. Actually, this is the max min. We're not involved in this. This is a max min. We're not involved. And how does goalie min? Yeah, that's the thing we're dealing with. This is the problem we're working on. This is a min-max problem. We want to solve this min-max problem. How does the goalie, which is the second player, minimize the kicker's maximum, which is the first player? Okay, and then the way it's done is that we will, this is the problem, min S2 max S1 of the game. Now, in order to do that, we realize that there are 4 different combinations. These are the combinations: L, 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 R, R, L, and R, R. Where this is player 1, this is player 2. There are 4 combinations, okay? Now, what is, and we're going to name each of them, each has a probability. The probability of player 1 going to left is S1 of L. The probability of user 2 going to left is S2 of L. So overall, the probability of LL happening is S1 of L, S2 of L. All right? Now, the probability of first player going to left is S1 of L multiplied by the probability of user 2 going to right, S2 of R. And similarly, the probability of first user going to right multiplied by the probability of second user going to left. And finally, the probability of first user going to right times the probability of second user going to the right. All right? Okay. Now, for each of these scenarios, we need to find the utility for which player? In other words, I'm going to find U of LL for which player? Ahmed Kadem Parhan Al-Rikabi suggests we are going to find the utility for user 1. That's correct. We want to calculate the payoff for kicker, which is player 1. So all of these is U1. All right? That's correct. Now, when both players go to left, what is the payoff for user 1? In other words, I'm interested in the value of this guy. The answer is 0.6. That's correct. So that's why I see this here. S1 of L, S2 of L times 0.6. That explains the first one. The probability times payoff, that's what gives you the expected value, right? The expected value is the sum of probability multiplied by quantity. Okay? So that's the first one. The second one is L1, LR, the first user going to left, second user going to right. What's the utility? That's right, 0.8, that's correct. So we have S1 of L times S2 of R times 0.8. Okay, that's good. And the next one, we're interested in RL. What is the U1 of R and L? U1 of R and L is 0.9. That's right, Wasam. So that's 0.9 times S1 of, I'm sorry, S1 of R, S2 of L times 0.9. That's right. And finally, RR. What is the utility for user 1 when both of them go to right? That's right. It's 0.7. Both Fatima was right, Ahmed right, Wasam right, Ali right. Ali Attai, I thought you were in a hospital. Yeah, 0.7 is right.
السلام عليكم دكتور.
وعليكم السلام.
Doctor, I didn't go last night. My son had a fever and stay up with him until
Oh, oh my God. I hope he gets better soon. How is he now?
now it's better. Alhamdulillah.
Alhamdulillah.
Thank you.
Okay, that's, I see. My pleasure. Anyways, so this is what we mean by the expected value of the payoff of user 1, which is the kicker. Okay, now we're supposed to do a min-max over this one. But before we continue with the min-max, we have to consider these conversions. So the probability of user 1 going to right is equal to 1 minus the probability of user 1 going to left. Similarly, the probability of user 2 going to right is equal to 1 minus probability of user 2 going to left. Are we good with that? All right. Excellent. So we're good with this. Now let's move forward. So first of all, we need to find the kicker's maximum. In other words, the max is done first. You see this? When they have min-max, you have to do the inside first. And then you do the outside. Okay, that's something you need to consider. In a min-max problem, you first solve the maximum, the maximization, and then you go after the minimization. In general, you do the inside first, and then you go take care of the outside. Okay, so we're doing this maximization here. And for this maximization, let's do it cleanly. Let's do a clean job here. Let's clean this up. Let's do it cleanly. Neatly. How do you say that in Arabic? And by clean, I mean orderly, in an orderly fashion. Organized. Masah. Tandif, I thought tandif is like physical cleaning. Oh, I guess it's used for both then. I mean, like you write cleanly, you write organized, in an organized fashion. You still use tandif? Okay, fine. Anyways, so we were here. The formula we had was here, right? We just copied this formula from here to here. Okay, this is where we are now. And then we did the conversion we talked about, this conversion. We applied this to that one. In other words, for so this one was kept exactly the same way. Whenever we saw S2 of R, we converted it to 1 minus S2 of L. Okay? And then whenever we saw S1 of R, we converted it to 1 minus, 1 minus S1 of L. S2 of R, 1 minus S2 of L. And here, S1 of R, this was converted to 1 minus S1 of L. In other words, we only need to determine one of the probabilities, going to the left. If we calculate the optimal probability of going to the left, it's done. We just do 1 minus that, and that'll give us the probability of going to the right. So that's why you see this conversion happening. All right? So now from here, we got to here. Let's take a look, see if you have any questions. Every probability of going to the right was converted to 1 minus that probability for going to the left. Are we good with this? All right, good. Okay. So again, in the minimax problem, we're dealing with the inside part first. So we're doing the maximization here first. All right. Excellent. So the maximization, as you remember, is on over S1. So we're maximizing, we're here. We're maximizing over S1 for this problem. So let's take a look here. Let's take a look. If we gather all the points for S1, what do we get? So we have, let's see. Let me type it. So we got S1 of L times what? Big parentheses, 0.6 S2 of L and then let's have a bracket. And then what else? There's more. There is there's 1 minus S2 of L times 0.8. What else? There's minus 0.9 S2 of L what else? There is S is minus 1 minus S2 of L times 0.7. That's all that gets multiplied by S1 of L. Let me just check. So S1 of L gets calculated by 0.6 S2 of L, gets calculated by 0.8 times 1 minus S2 of L, gets calculated by, what should we call it? Gets calculated by minus 0.9 S2 of L, and finally gets calculated by minus 1 minus S2 of L times 0.7. So that's all I see for S1. So if I simplify this, what do I get? Well, there's more, of course. There's S2 times something. There is plus S2 of L alone being multiplied. So 0.9, so plus S2 of L multiplied by minus 0.9 and then minus 0.7. Oh, wait, maybe I'm missing something. No, that's plus. This is plus. Yeah, that's right. So plus 0.9 minus 0.7. Yeah, that's more like it. Yeah. Okay. So I can actually put this here. I can make this bigger. And plus this. Okay. So now I can further simplify this part. Now I'm gonna do that right now. I guess I could do 0.6 S2 of L. We got minus 0.8 S2 of L. That gives us minus 0.2 S2 of L. Right, minus 0.2. And then we got minus 0.9, which gives me minus 1.1. And then there is plus 0.7. So that gives me 0.4 S2 of L. So let me write it down here. Equals S1 of L times open accolade 0.4 S, well, minus 0.4 S2 of L. That's for that. Okay, what else do we get? Besides that, there are constants here. So we have 0.8 over here, and then minus 0.7, so that gives me plus 0.1. So, well, it looks like we got what the guy is saying. So that's for that. And then this one is S2 of L times 0.2. Okay, so we got what the guy is claiming. This is what we get. After simplification, we get exactly what he's saying. And then there's one there's one more term. There's a free term that we actually need to take a look. So we got 0.9 here, right? Constants are 0.9 and then 0.7. Wait a minute. So there's 1.7 here, and then no, so that 0.7. Yeah, I only see a 0.7. So that's what it is. Plus 0.7. Yep. Okay, yeah, that's it. Need to add it here as well. That is the only constant that I can see. Yeah. Okay, so how are we going to maximize this with respect to S1? Any suggestions? This is a function of S1 of L, S2 of L, and we're supposed to maximize this with respect to S1 of L. In max, he derives with respect to S1. So Ahmed is trying to say we should take the derivative of this function with respect to S1 of L. That's good. That's good. So we're going to take the derivative with respect to S1 of L. And if we do that, what's going to happen is that we're going to take, so if you take the derivative here, the derivative of this function with respect to S1 of L would be the coefficient of S1 of L, which is minus 0.4 S2 of L plus 0.1. And that's going to be equal to 0. Yes, we consider S2 constant. Excellent, Wassam. When we're taking the derivative with respect to one variable, we consider all other variables constants. That's why they act as a constant. They vanish. They become 0. Okay. So that's for that. And then, what would that give us? It would give us S2 of L equal to 1/4. That's exactly what we got. 0.1 minus 0.4 times S2 of L equals 0. Therefore, 0.4 S2 of L is 0.1. And then S2 of L equals 1/4. Okay. All right. So if S2 of L is 1/4, then S2 of R is 3/4 because it's 1 minus S2 of L, right? So we're good. So in the first part, by doing a maximization over S1, we concluded that S2 of L is 1/4 and S2 of R is 3/4. Any questions so far? All right, I guess we're good. Okay. Um, so shall we solve the same thing for max min now? I think that's a good idea, huh? I think it would be a good idea to do that. But I want to make sure everybody understands so far. If everybody understands so far, we're going to go back to solve the max min now. This was min max. Let's solve a max min. Okay, let's go back to this part. Let's do a clean job. Let's clean it up. Okay, so to solve the max min using when we played multiple times, we call it mixed strategies. We're going to do it this way, just like the min max. We're going to start with different. We're basically doing what? How does the kicker maximize his minimum? So kicker wants to maximize his minimum. Now, it means if the goalie plays in such a way that minimizes kicker's utility, how would the kicker maximize his minimum utility? Okay, so again, we're going to do all different combinations, LL, LR, RL, and RR. And again, we're interested in the payoff of kicker. We're dealing with that. Okay, so before we go there, first we need to say the probability of each of these. Okay, so first player going to left is S1 of L. Second player going to left is S2 of L. First player going to left is S1 of L. Second player going to right is S2 of R. First player going to right is S1 of R. Second player going to left is S2 of L. First player going to right is S1 of R. Second player going to right is S2 of R. Okay? Now is the time to ask the question from you. What is the utility of the kicker, which is the player 1, when both of them go to left? So first of all, what number should I write here? What utility I'm dealing with? So the utility of left, left for user 1 is 0.6. That's correct. So what I was going to ask is, this is 1. So you're right. I think you got it all right. Yes, Ahmad Kadam mentioned it as 1. Okay. And everybody else said 0.6, which is also correct answer. Good. Now, the next one, utility of user 1 when user 1 goes to left and user 2 goes to right is 0.8. Fatima is correct. And so is Aya and Wasam. All right. Now, the utility of user 1 when user 1 goes to right and user 2 goes to left. So user 1 goes to right, user 2 goes to left. Yes, 0.9. You're becoming fast, guys. Good, good, good. Everybody, good job. Everybody, good job. Now, how about the time when both players going to right? Yes. When both players go to right, the utility for user 1 is 0.7. Okay. And then, obviously, we have, we need to multiply that by the probability. That's why we have this value. S1L, S2L, 0.6. S1L, S2R, 0.8. S1R, S2L, 0.9. S1R, S2R, 0.7. Okay? So again, because it's a max-min problem, we still need to solve the inside first. So we're going to find the minimum over S2 of this whole thing. However, there's an intermediate step we need to take care of. What intermediate step is that? Can somebody tell me? At this stage, I got S1 of R, S2 of S2, S1 of L, S2 of R, S2 of L. There's something I need to do before I can take care of the minimization. Can someone point that out? MashaAllah, Ahmad Kadhim. Ahmad Kadhim, MashaAllah. Well, I'll take it back. It's not S2 of R1 minus S1 of L. It's S2 of R equals 1 minus S2 of L. The same user. The probability is only for the same user, yes. How do you say good job, well done in Arabic? Ahsant? Well, other than Ahsant, yani. Oh, you say Aywalla, right? Yeah, you say Aywalla. Mumtaz. Mumtaz also. Okay, good, good. Got it. Okay, good. All right. Now, I'm going to convert every R into L. So S2 of R becomes 1 minus S2 of L, and S1 of R becomes 1 minus S1 of L. Okay, with that, we do another round of cleaning. Okay, if we do that, if we convert S1 of R to 1 minus S1 of L, we get this as this. Right? Am I right? No, that was not it. We get this as this. And then we get this as this. And we get this as this. Okay? So everything will be in terms of the left probability. As long as we have the probability for going left, we can easily calculate the probability for going right. All right? All right. So next, I need to simplify this. Just like the previous problem, I need to simplify this. So again, because this is going to be an optimization, the inside is min of S2, I need to write everything with respect to S2 first. So it's going to be like this. S2 of L times, open bracket. First we got S1 of L times 0.6. Then we got minus S1 of L times 0.8, right? And then what's this guy? Oh my God, can I get rid of this? Then we got, for S2 of L, we got minus 0.9 S1 of L. And then we got plus 1 minus S1 of L times 0.7. Okay, there's a mistake here. This one would be 0.9 times 1 minus S1 of L. Yeah, that's right now. Do you see how I do this? Or you need further explanation? So this is now minus, actually. Okay. So that's for S2 of L, anything that's multiplied by S2 of L. There are other terms here that don't have any S2 of L in them. They just have S1 of L or constant. Let's find those. Those that only have S1 of L. Can someone show me one term that only has S1 of L here? Let me show you how I find it. Only S1 of L would be this. This times this. Oh, sorry. This times this. And then times this. That would give me 0.8 S1 of L. So I'm going to write it here. After I'm done with S2 of L terms, I close the bracket plus 0.8 S1 of L. Now, what else? There's more. There's another one that only has S1 of L in that. It would be this times this, and then times this. So that would give me minus 0.7 S1 of L. Okay? So that would essentially be 0.8 minus 0.7 times S1 of L. Right? Now, I need to also look for terms that are purely constant. Purely constant terms would be like this guy. 1 times 1 times 0.7. Let's see if I see more. No, there's no more. That would be it. Plus 0.7. Okay, let's just double check everything. How many terms we got? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, no, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's right. So this one's right. Yeah, this is good. Now we need to simplify this. So this is going to be equal to S2 of L times, we got 0.6 S1 of L minus 0.86 S1 of L. So that would give me minus 0.2 S1 of L. And then we got 0.9 S1 of L, which gives me plus 0.7 S1 of L. And then we got minus 0.9. All right? And then there's more, sorry. Minus 0.7, that gives me 0.2. And then we got plus 0.7 here, so that would be 1.4. That's interesting. Let me just check everything is all right here. So that would be plus 0.7 here, plus 0.9 here, that gives me 1.6, minus 0.8 here, which gives me plus 0.8, yeah, that would give me 1.4. Okay, interesting. So how much constant do we get? It would be minus 0.9 minus 0.7. Okay. Oh, that's interesting. Minus 0.9 minus 0.7. That is really interesting. All right, so I need to double check one more time. I'll start over. S2 of L times S1 of L 0.6, okay. S2 of L times minus 0.8 S1 of L, that's right. S2 of L times 1 minus, okay. That's what I got, yeah. So this is the problem. This is point plus, okay, that was it. So plus 0.9, 1 minus S1 of L, that's right. And then eventually minus 1 minus S1 of L times 0.7. Yeah, this is good. And then I got for simple term, well, no S2 terms, I got minus 0.7 S1 of L, and then plus 0.8 S1 of L, okay, and then we got 0.7, yes, so that would be it. Okay, good. Okay. All right, so let's simplify it now. So now we got S1 of L 0.6 and minus 0.9, which gives me minus 0.3. And then we got minus 0.8, which gives me minus 1.1. And then I get plus 0.7. 7, which gives me, one more time, that would be 0.6 minus 0.8, which is minus 0.2, minus 1.1, and then 0.7, which gives me minus 0.4. Okay, good. And then the constant terms. We got 0.9 minus 0.7, which is 0.2. So plus 0.2. Okay, that's more like it. Yeah, that's good. We're good. We're good. And then we have 0.1 S1 of L plus 0.7. So this is the simplified version of the above. Okay, now I need a brave volunteer to tell me what we should do next. Ahmed Khalid.
Yes, doctor. Now we derivative
Okay.
S2. Derivative S2.
Okay, good. Okay, great. So derivative with respect to S2 of L. And what would be that? What would be the result? If you take the derivative with respect to S2 of L, what would be the value?
Doctor, minus 0.4 S1 L plus plus 0.2.
That's correct. That's right. Okay. And we set that equal to 0, right?
Yes, doctor.
So what would that give us as the optimal S1 of L?
It's half.
That's right. So the best strategy for the kicker is to go to the right, shoot the right side 50% of the time, and shoot the left 50% of the time. All right? So if we review what we did so far, it's like we should solve min-max and max-min to find the best strategy for each of these two players. Okay. So S1 of L was found to be 1/2. Okay, good. Okay. All right. So we did a min-max and a max-min, and okay, what it's saying here now is saying for two players, min-max is solvable with linear programming. And this is what that means. And we're fine. We don't need to go for it. Okay, next topic is correlated equilibrium. It's just some intuition. Consider again battle of the sexes. Intuitively, the best outcome seems a 50-50. Ali, what do you want to talk about?
Excuse me, doctor, before we start this new subject, can I ask a question about another subject that we take? I need from you to explain to me more because I have
Sure. What is it?
understanding about this. Victor, it's
What is it?
about the dominant strategy. Uh,
Okay, let's go back.
page 29.
29.
Here, Doctor.
Uh-huh.
Doctor,
Uh-huh.
the M was dominated. Uh, can you explain to me why we move the row of M?
Sure. So let's go back, start from the beginning, from the very beginning. Iterated removal of strictly dominated strategies. So let's compare for, let's see. So let's see if anything is better for user 1. Let's compare for user 1 if we have a dominant strategy. In other words, we're comparing the rows here. And then we're comparing these. Right? That's for user 1. Now, for user 1, it looks like that there is no dominant strategy. I mean, at least I can't see it. Like, if I compare U and M, I see that sometimes U is better, sometimes M is better. So I can't really say someone is dominated by something else. When I compare U and D, the same thing happens. Sometimes U is better, sometimes D is better. And when I compare M with D, exactly the same thing happens. None of them is completely dominant. So for player 1, we can't really remove anything in the to say it's dominated by something else. So we go after player 2. Player 2 now. And we're going after player 2. We need to compare column-wise. And then we also need to compare the second one, which is the payoff for player 2. Okay. Now, when I look at this, I realize R is dominated by C. R is dominated by C. Don't you agree with me? Because 0 is less than 1. 0 is less than 1, and 1 is less than 2. Right? So I can get rid of R. So now my new table is going to be this. I got rid of R. Ali, do you have problems so far? Are you okay with this? All right. Now, when I compare, again, if I look at player 2, there is no dominant strategy here, right? If I look at player 2, these will be compared together, and they're all the same. So there's no really dominant strategy if we start with player 2. However, if we do player 1, now, after R is removed, we're looking at these rows, and then we're looking at the first element, because we're interested in player 1, and it appears that 4 is greater than 0. Well, I wanted something better, I guess. Let's see, let me just, maybe I get a better one. Wait. Slightly better. Well, 4 is more than 0. 1 is equal to 1. So that won't work. Oh. Wait. I'm sorry. That's not what I should have been doing. I should compare. Let's compare. Okay. That's interesting. Wait a minute. Let's remove. Interesting. Well, I don't understand what you're saying, Ali. Multiplied by 1/2? I don't get it.
Yes, Doctor. From they multiply user 1 and 1/2 and user 2 and 1/2. And user 1 and 1/2 for U and D. And see which one the bigger number, the result is bigger number. For
Why do you say 1/2? Where did it say? Where did it mention 1/2?
1/2 multiplied by 3 for user 1 and 1/2 multiplied for 4 for user 1.
Why should I multiply by 1/2? I don't understand. By 1/2. Why do you say 1/2?
Doctor, this is that's my question, Doctor. And
No, nowhere in the page talks about 1/2. Nobody talks about 1/2. You're saying 1/2. I don't see anything 1/2 here.
yes, Doctor.
You shouldn't talk. Well, let's see. There's no 1/2 here, though. There's no 1/2. You should look at the gains. That's what we're doing here. Just compare the gains. If user 1 plays U, it gets 3. If user 2 plays L, it gets 0 if user 2 plays C. So these two aren't, there's no dominant over there. I don't see anything dominant here. Interesting. I see. So user 1, I don't find anything dominant. But let's see.
Excuse me.
Yes?
In the previous example, before this page.
Uh-huh.
Also before this page, Doctor. Yes, this example.
Right.
Okay, this example.
Well, this is in the middle of example. This is in the middle of example. It's not really an example.
No,
well, we could still continue this, but that's fine. Yeah, go ahead. What's your point?
Because in that example, we cannot dominate U by M or D. So we.
Oh, I see. Okay. So you're saying in this example, what happens is that we're stuck at here, huh?
Yes, Doctor.
Okay. Okay. I see what you're saying. So let's go back. So Ali was talking about page 29, right? This is page 29, Ali?
Yes, Doctor.
Okay, so M is dominated by the mixed strategy that selects U and D with equal probability. Can use mix. Oh, that's what you mean by 1/2. Okay. I see what you're saying. Okay, so this is actually, we didn't teach this part though. We never talked about dominant strategy by mixed strategies. We didn't teach that in the class, but if you want, we can discuss it now. I see. Can use mixed strategies to define domination too. We could do that. If you want, we could talk about it. So, but I never discussed this in class. In the class, we only talked about dominant and non-dominant. That's it. You want me to think about this and talk about this? Because if I talk about this, you will be asked about it in the exam or in the homework.
Okay, doctor, I just need to understand it because I looking for it in the YouTube.
Okay.
You speak about the half, and I told you about this half, and I have a
Okay,
misunderstanding
good.
of this.
So again, we didn't teach this, but I'll briefly explain this. So it says M is dominated by the mixed strategy that selects U and D with equal probability. In other words, if I define a new row here, which is a mixed strategy that selects U and D, then you get 3 halves plus 0 over half, that's 3 halves. 1 half over 1 half, 1 half plus 1 half is 1. And then 0 plus 4 over 2 is 2. And 1 over half, 1 half plus 1 half is 1. Now this is mixed U and D. Okay? Now mixed U and D dominates M. In other words, M is dominated by mixed U and D. Remember, we cannot use U and D. We cannot compare U and D with a mixed U and D. We only compare M with mixed U and D. Okay, that was a good question, Ali. So now M gets dominated by mixed U and D. You see how that happened? 3 halves and 1?
No, doctor.
No?
It's not obvious to me. Mixed UD.
Okay, I'll show you. So this is 3, right? This is 3. And this is 0. If I play U 50% of the time, 3 times P of U plus 0 times P of D, that gives me 3 halves plus 0, which is 3 halves. That explains for this 3 halves. Then go after one and 1. Now 1 times P of U plus 1 times P of U, P of D equals 1 half plus 1 half equals 1. Okay? That explains for this guy. Now, I could go after this guy. This guy, that would be 0 times P of U plus 4 times P of D. That would be 0 plus 4 divided by 2, which is 2. That explains for this 2. Next, we have this guy and this guy, which is 1 times P of U plus 1 times P of D, which is 1 half plus 1 half, which is 1, and that explains for this 1. So if we do a mixed U and D, these will be the gains in average. And if we define a strategy, not an action, but a strategy, which is mixed U and D, then M is dominated by that.
Yes, doctor.
As a matter of fact, that's, yeah, so that's it.
Thank you.
But the book, no problem. Yeah, that would be it. I guess we don't have any other questions, and we just review what he was saying in this slide, which was just intuition. Nothing really correlated equilibrium. Intuitively, the best outcome seems a 50-50 split between F and B, but there's no way to achieve this. So either someone loses out, or both players often miss coordinates. Consider again the battle of sexes. Intuitively, okay. Now the traffic game. What is the natural solution here? A fair randomizing device that tells one of the agents to go and the others to wait. Well, I guess we could wait until next session for this. That's fine. All right, this concludes the class. For your next class, for data mining, I need everyone to have his laptop with him, okay? Bring your laptop for the next class. I need you to share your screen, okay?
Sorry, Doctor. Doctor, did you hear me?
Yes.
Doctor, please, some of command work, but another command it does not work.
Yeah, we're going to talk about this in the class, okay? Bring your laptop.
Okay, Doctor. Okay.
مع السلامة.